Good afternoon. My name is MENDEZ-RIOS, and I'm going to be discussing the project number 3 of the class Computer Networks. The idea of the project is to be able to solve the shortest path routing problem. For this, we're going to be using Jupyter Notebook along with Python and some other libraries like NetworkX, which will allow us to develop the graph and visualize the graph component of the network. We're going to be using matplotlib to plot said graph. We're going to be using NumPy and pandas and sklearn to generate other metrics for evaluating the model, as for example, getting uh, the mean value of it and stuff like that out of the weights. These are all things that will help us better visualize the problem before we tackle it. As for the possible algorithms that can be used for solving this problem, there is Dijkstra, Floyd-Warshall, Bellman Ford, and A-star. A-star is the one that we're going to be implementing, and soon it will be explained the reason for this. Here we are just importing all the necessary packages. So the graph or the network graph that we're going to be working with can be created using NetworkX graph. It would be a weighted graph with only positive weights. This does simplify the problem at some extent. We can see all the connections and how uh, they, they interact with each other in this graph. For better simplicity or for better visualization, this is another graph that we have. In this one, it is visualized as um, the graph that has more than the mean value of the median value of the of all the weights. Are anything above it is gonna be black. Anything below it is gonna be purple. That way we can visualize better which of these links are weight less and which ones have more weight. As for more analysis for the graph, we can calculate, for example, the amount of nodes and edges, or the amount of, uh, well, in this case, these are terminals and their connections. We can see, for example, that there is a total amount of 22 connections between the 14 nodes. Uh, there are roughly twice the amount of edges than the amount of nodes. And from some previous analysis that was done in the project, we were able to calculate or better analyze the time complexity of each of these algorithms. For example, we have that the algorithm of Dijkstra has a time complexity that it's square the amount of vertices that there are, or the amount of nodes. The There is another simpler, more optimal way of implementing Dijkstra. Even that one has a value of 111 given the amount of edges and nodes that we have. From this analysis, we can see that A star would be among the most efficient, even though we have a dense graph. In other words, that there is more edges than nodes. This difference is still not enough for it to be for any model that only depends from vertices be faster than those that depend of the edges. Here we can see that any model that depends of the vertices is substantially slower than the A star, which only depends from the amount of edges that there are. All of this, of course, depends on the heuristics of the model, or which heuristic distance we're using to calculate the A star, since A star itself is an heuristic greedy algorithm. Over here, we are testing out how we can turn from well the graph into an adjacency list. The adjacency list is going to be a type of data structure that we're going to be using for representing our graph, where we have that each key holds the connections, the direct connections that that key contains, and its respective weight. From here, we can start to develop the implementation. We we're gonna be using that previous implementation of turning the graph into an adjacency list within our init. That way it's already initialized once we create the graph component. And we're gonna be, this function is gonna be the one that will be retrieving which are the neighbors of said node. For example, the node of Washington has as neighbors, well, California 1, California 2, and Illinois. The heuristic function currently is a very simple heuristic of a constant value of 1 for all the nodes. This in a way turns it into something somewhat similar to a Dijkstra algorithm. There are other heuristics that can be implemented to facilitate the distance. However, they all depend on the type of data that you have. Uh, some distances can be the Manhattan distance, Euclidean distance, but they tend to depend of an XY measurement, and currently we're not really working with an XY measurement for each node. We just working with a direct distance. Now we can start developing the A-star algorithm. We start by creating, well, the set of values that we're gonna be working with. The first is an open list, which will hold all the visited nodes, and we have the closed list, which are the list of nodes that have been visited and whose neighbor have already been inspected. For open list, we haven't inspected them yet, so they tend to first be fall under the open list, and once they are analyzed, we put them in the closed list. The G dictionary, on the other hand, contains the distance between the current node, or well, the starting node, and any other node that is in the map. This will simplify the retrieving the value of what will be the total distance traversed by the algorithm. And we initialize the we give the initial value with the start node of 0. Some algorithms implemented with infinite value, but right now we're just, if we haven't studied we haven't traversed the node yet, we're just not gonna add it to the list. And there is the list containing the parents of each adjacency map for all nodes. Afterwards, we're just gonna be looping through all the values on the open list. In other words, the value that we haven't analyzed yet, and we're just gonna go through each node and be calculating its heuristics. And if that heuristics turns out to be smaller than the previous one, then we just set that new value, the new node, to the next one. This aspect here just works by stopping the algorithm once we have reached the or the goal or the stop node, and we're just gonna start reconstructing the path backwards from here and returning that reconstructed path that was created backwards and return the traverse time or the traversed weight, the total traverse distance. And here it's an algorithm that will, well, the part of the algorithm that goes through all the values of the open list. And if the value is not in the open list or in the closed list, then we add it because it means that we still have, it's a new value. And then we calculate its weight with respect to the starting node. If that value is already in open list or closed list, meaning that we have already seen that value while traversing the graph, then we verify, okay, is that value uh, bigger than the previous one? If so, then it just means that we have to change the previous value. If the value is in the closed list, meaning that we already traversed through it, we remove it and then we add it to the open list in case, because that would mean that we haven't fully seen all the all the possible outcomes that can go towards that node. If the open, like for each loop, we're gonna be clearing, like through the loop, we're gonna be clearing the open list and adding it to the closed list, meaning that, well, we have finally traversed through all of the possible routes that can lead to that node. So once that happens, we remove it from the open list and we add it to the closed list. If there is a case where this loop finishes without entering the stop node, it means that, well, the path doesn't really exist. In the case where end ends up being none, it also returns a path does not exist. This means that if we reach the end of the list or something without actually reaching the any stop node, it means that probably the stop node is not really in the graph. And over here, we're just gonna be testing that algorithm with New Jersey, like with the route between New Jersey and California. And it turns out to be, well, this route right here. This go from New Jersey to Michigan, Utah, and to finally California one. It's a total of 3,450 points or weight. And afterwards, we decided to actually just compare that algorithm that we built, which kind of has a very odd heuristic method, with, well, uh, the one that is already implemented by the Network X. Uh, so to get the A star from Network X, we just call it A star path from the module. We give it the graph, the starting node, the end node, and that should return us, well, the list of traversing. And to get the length from that traversal, we just use a start path length with the same parameters. Over here is just testing out the that each of the algorithm. So testing out the algorithm that we implemented from scratch and comparing it with the one implemented with networks X and module for the desired inputs that were given by the project. The results are actually the same as we can see, and it gives it means that the algorithm is working as it should be. This should be a good this is a good result. If we compare, for example, uh, from New York to California 2, this is the path taken: New York, DC, Texas, and California 2. And using an X, we get that very same path: New York, DC, Texas, and California 2. And we get the very same total traversed ways. This would be the final implementation of A star from scratch and comparing it with, well, a pre-implemented A star algorithm. Since this is an heuristic model, one way that it can be highly improved is by fixing the heuristic function. Giving it a better heuristic might actually give faster results, but it would not really uh, give any different results than the previous ones. So everything would, any improvement done to the heuristic function would just be to increment any time complexity that could happen. And yeah, that will be the end of the implementation. Thank you very much.